Okay, let's start. So today the plan is to continue the discussion about the hardware layer. Again, what we will discuss about reduced precision is also uh, interesting, important when it comes to model compression, right? Today is mainly talking about this reduced precision representing both weights as well as the activations with some reduced precision in order to save energy and so on. So the benefit that we get out of this reduced precision, and again, this is by reduced precision, I mean there's a specific representation that you have for these digits, right? So the default is using some floating point numbers, right? Floating point variables like 64. This is by default is used. You want to reduce it to like 32 or even like integer representation. So you get some reduced precision. Obviously, as a result, you need less storage. Also, we'll discuss that this will result in some reduced energy consumption and improves performance. But on the other hand, you need to make sure that you don't lose any accuracy because you don't want to mess up with the mathematics and get a basically train a bad network that doesn't give you the accuracy that you wanted to have. So it's again talking about the trade-off space, and essentially this is what we discuss in more detail when it comes to model quantization and compression. These are the building blocks of basics why we get these benefits out of this reduced precision. Before we go into the detail, do you have any question about this? So again, this provides a trade-off space between, even like you can consider multiple objectives. Obviously, in one hand, like you want to get same accuracy, right? But also you're talking about the energy, right, and storage. So you want to have benefits of all of this by this reduced precision. And if you think about like the kind of operations that we had specifically for dense network, you remember we had some weight matrix that this was large size for this dense fully connected network. You had some activations. This was your input activation, and you had some output activations, right? So we had some operations. You had also need to sum all of this. So you had this dot product plus sum to generate each of these values in the output activation vector. So this was basically what you had, and you pass it through some nonlinearity to generate this output activation. So these are the key operations that you're familiar with. And then when it comes to training, you also need to update the weights. So you multiply this activation also with this gradient that you calculated. You multiply it by some learning rate, adding to the previous weight in order to update the weight. So these are essentially what you are doing. This is for generating the activation, right? And this is for updating the weights. So these are essentially like whatever operations that we need, or kind of computation that we need for such network. And the question is that, like, why representation matters, right? Obviously, different representation provide different precision or accuracy in terms of representing the actual numbers, right? Because like we are talking about the computer, and you know that like in mathematics, in abstract way, when you have a number, you're talking about the absolute precision, right? But when it comes to representation, representing these actual numbers in computer, you don't have that absolute precision that you get in mathematics. So you get some accuracy. So in floating point 32 bits, for example, right? So you get some bits for exponent, the actual thing, and the sign, and this representation, the whole thing would give you the precision or a range of values that you can represent between roughly around over 70 orders of magnitude, essentially, with this 32 floating point number, and you get this accuracy or precision, which is quite large, right? So, and when it comes to floating point 16, obviously you have 16 bits to use for representing the floating point numbers. The range is a lot smaller, and you know that, like, these are, I don't want to go into detail, I assume you know these basic things, how these ranges are represented by using these representations. So these are, you already have learned in previous courses. But essentially, the takeaway is that when you have a smaller representation, and in your programming language that you use, Python, C, C++, you have API classes that you can use for each of these representation. So obviously the accuracy would be smaller. For integer values, then these are fixed values with exact same space between these values. For 32 integer representation, then this is the range that you cover, and you know that for integer, the actual precision that you have is exactly the same. So the difference is that here, so when we are talking about the accuracy, that you know that, like, when we have a smaller values, right, from negative, right, from, like, let's say from very small value, so from 0 to whatever value that you can represent, right? So when you're approaching to the upper end with a floating point, or you're approaching to the lower end closer to 0, the actual precision that you get would be different when it comes to floating point. But for the integer values, it doesn't really matter where you stand. So all the time you have a fixed a space between each of these values that you can represent with this structure, because these are integer. The same for lower precision integer. You get exactly the same accuracy based on this integer, but obviously the range of the value that you can represent would be totally different. Do you have any question about this? So with different representation, you get different ranges with different accuracy. But the important aspect is the cost of these operations. When it comes to mathematical operation that you do, and the mathematical operation, you need to have three things, right? Multiplication, right? So you have multiplication, you have addition, right? And you have a read from memory. So you have essentially three different operations that you can do. Your computer for any sort of calculation, including neural network. And you see that the interesting point, these numbers, the relative energy costs are very interesting. So some observation that you can see here. So if you focus only on these two, right? So this is 32-bit floating point multiplication, 16-bit floating point multiplication. So essentially these two, the difference between 1.1 picajoules to 3.7, roughly around 4 times higher. You pay the energy consumption when you do multiplication in 32-bit representation. So that's why it matters, and what kind of saving you can get if you reduce the precision. You can also see even higher when it comes between 32 to 8 bit representation from this number to 0.2. So like the relative values are, this is for basically for integer. The relative value of doing multiplication between 32-bit representation of integer is even like higher. It's roughly around 15 times higher, the difference between these two, right? The addition, so these were about multiplication. If you look at the addition, then the difference between 16-bit and 32-bit floating point addition, not as before that you had in multiplication, maybe around like 2 times higher, but even this higher is dominated by, if you compare this guy with this one, you see that the cost for addition is smaller than the cost for, sorry, this one, the cost for multiplication. So multiplication essentially is much more expensive task in your computer. And compared again these two integer operation with these two. So again, a lot smaller, relatively speaking, with respect to the multiplication that you have. And if you want to also compare it with the memory read and write, you can see that the most expensive operation that you have on your computer is retrieving these digits that you stored in memory for doing the operation, because like you have this data, this data basically essentially what you have are the weights and the activations. These are, you need to store it in memory. So these are the most expensive operation, and essentially your SRAM, the operation is, you see that even in SRAM, which is basically on-chip type of memory with off-chip type of memory, DRAM. DRAM, you see that like off-chip memory is the most expensive operation that you can do. So anything that goes like beyond your chip is very expensive, and this is like comparing the other ones is several order of magnitude higher, right? So you already see this difference. 2 orders of magnitude are higher, even comparing with this on-chip type of operation. And obviously each of these representation has some cost, because specifically these we have two dimensions when it comes to chip design, right? Like the area cost. This is what the area based on which you build your chip. So obviously for higher precision, you need higher, larger area to create this chip. It also affects the energy consumption. So you have basically 2 dimensions. One is area and one is energy. So and you see that already the difference in terms of area for different operations that you have. So basically, these areas are essentially your PEs which are connected to each other. You have a mesh of PE, right? But anyway, some of those who have gotten the architecture, hardware architecture, you already know what I'm talking about. So essentially, if you think about the hierarchy of memory, so in your computer, you have some hierarchy, right? So and the locality matters. So you see that if you have access to your local SRAM, you pay for each access, you pay 5 picojoules, right? If you go to your on-chip SRAM, you get basically 1 order of magnitude higher comparing to your local SRAM. The difference between these two are maybe obvious here in this diagram. So these are, you have for each processor, you have some core, right? For each core, you have some local SRAM. These are basically for each of the core that you have, and you have some on-chip SRAM for all of your cores, right? So this is shared across all of these processor cores. And you have some off-chip DRAM. This is the most expensive operation that if you want to all the way go to your DRAM, right? So essentially this gives you an idea, like this is, both of these are on the chip. This is associated to each core. You see that this is the least expensive, 5 picojoule. Again, like the least expensive relatively for any memory access. Obviously, it is higher if you compare it with any multiplication. So the least expensive memory access is, in terms of energy consumption, consume more than even like the most expensive mathematical operation that you want to do. So these read access, memory access are very expensive. And if you go higher and higher, obviously you know that this, if you go higher, you get larger memory size. This become expensive, and if you go to your DRAM, external memory, this becomes very, very expensive in terms of energy consumption that you need to pay. And that's why some type of new accelerator, specifically for inference, they have this locality feature that for each of these, you get some inference core that have this integrated local memory, local core to store activation and weights locally for each core, inference core. So these are explicitly managed, essentially. Do you have any question? Let's look at if we now we understood, okay, with different precision, it has some influence to energy consumption. So we have like this gives you an idea. We have different operation for doing the either inference or training task. Since we know that each operation are consuming different sort of a scale of energy, then go into the detail of these operations, see what are the opportunities and make it much more concrete. So essentially here what you see is the operations that you need for doing inference, essentially calculating this BI. This BI, if you remember, was the output activation. This AJ was your input activation that you needed to multiply it with weights, right? So you had some weights. For this, obviously, you need to access memory to retrieve your weights. And then you had this activation, input activation, you need to multiply this, and then you need to add this together in order to calculate this output activation. So these are the operations that you have essentially for inference, and you can think about it like one way to make this exploit the usage of knowing this knowledge that each operation provide different cost, impose different cost, then you can design the right way for these operations that decrease your cost. For example, these weights, we know that we need to access memory, and if like these are like, again, a fully connected network, like you have 16 millions of these weights, then even you cannot store them like in your on-chip, and sometimes even you need to store them in your DRAM, external memory. So you want to have the lowest possible quantization for these weights, and like one way to do that is trained quantization. We'll talk about it later, but you can consider the lowest possible precision, like 4 bits representation for each of these weights. And then like once you have it, retrieve it locally, you can decode it to get higher precision, like 16-bit. You can store this activation as 16-bit, and then you have a 16-bit to 16-bit multiplication, and then basically you can accumulate all of these 16-bit multiplication and accumulate it to something like 24 or 32-bit output, and you know that so let me ask you this question: why this scheme makes sense? Do you have some thoughts? How you can make sense out of it? Like why this representation? Why not the other way around? Why? And you see that you see some mixed precision, right? You use different precision for these weights, use different precision for this activation, and then you use different precision even for accumulation of this. Why this makes sense from what we have discussed?
My intuition would be that the weights are something that you have a whole lot more of than the activations. Mm-hmm. And because we have a lot more of them, we want to use a lower precision for those.
Okay.
Because that would give us, I guess, less DRAM, access, or we would be accessing memory far less with those.
Okay.
But then the activations, I guess, the information stored in the activations is more important in some way, maybe more useful in training or in inference, I guess.
It's just more important, or like you can interpret it. It's just more important, or you have some other idea, like why, for example, you want to use higher precision for this rather than the weights themselves, right?
I mean, I guess we would get less benefit using, say, 4 bits for the activations, because the activations we don't have nearly as many of, like nearly as much, like we have far more weights than we have activations, right?
Exactly. That's the case, right? So you remember you had this thing, right? Where is this? So the activations are small comparing with this giant thing, right? So the whole thing, right? This is giant. You take it, you put it on your DRAM, right? This is off chip, right? And this is very expensive, right? And like you have no way to like store the whole 16 million or even more weights in your local memory. So you want to like have the least precision as possible for these guys, right? To make them like a lot more efficient with respect to accessing this DRAM, right? Because this is very expensive, right? But relatively speaking, these are a lot smaller, and you could consider having a higher precision for that, right? So this is kind of the way how you want to think about it. And once you retrieve this, so you store this with like 4 bits. Once you retrieve this guy, you want to multiply by this guy, right? And then you can decode this to 16-bit. So having the same precision at this guy for multiplication, because you don't want to have mixed precision when you do the multiplication. And you can decode that once you retrieve it locally, because you retrieve part of it. You don't retrieve the whole thing. retrieve part of it locally. Once you have it locally, you do this multiplication with 16-bit precision, right? But why you want to have like higher precision here, and why it makes sense?
So if there's quantization error with the weights, you can actually factor that into the training process because you learn the weights, whereas the activations change for each inference. And so you really need high precision for each inference in order to consistently not lose accuracy. Does that make sense?
And this is I mean this is only inference, right? We'll talk about training shortly, right? Here, but when you accumulate the weights, but this is only for calculating basically the output activation. Somehow the explanation you said makes sense, but do you have some other thoughts?
Well, I'm just thinking that the loss of accuracy that you would get from reducing the weight bit size is something you know about during the training process. So you know about it in advance. Whereas when you do that to the activations, it's not clear in the training what will happen in the test set.
Actually, it's not really about this, miss of accuracy when you have in your training. Let me maybe. Does anybody have any other explanation for this before I answer it?
I mean, I was figuring that's just because the output there is the activation for the next layer. So we would want to maintain, for the same reason that the activations are stored as 16-bit, we would want to accumulate them to the same or higher level precision, because those are going to be used with another layer, with the next layer, with a set of weights. And then eventually as an output, we might actually just want higher precision.
But like the output, like, I mean, like the output would be the input of the other layer, right? So like this guy would become this guy for the next one, right? So at the end,
right.
At the end, we need to convert this guy, if we use 32-bit, to reduce precision to 16-bit when it comes for the next layer. But like when it comes for accumulating those, why we want to use like higher precision, right?
I mean, isn't that, I guess, in some way necessary when we're, I mean, we've got a 16 byte by a 16 byte multiply. So we need those bits, at least to begin with, just that we need that space to begin with just to actually multiply those two together without, I guess, I mean, you could just lose the precision. And if you're going to, is there something about like precision here where we're like, if we accumulate it to a larger set of bits, and if we somehow squeeze that down into 16 bits, that we somehow maintain more information? I don't know if I'm making any sense here.
No, it makes sense. So like going back again to this diagram, right? So two things, right? So we have this sum, right? Basically for calculating these guys, right? You have this sum, right? That is going through your your rows, right? Essentially here you have this guy, you calculate it, and then you move here. Next guy, you retrieve it from your DRAM. You do this dot product, and then you need to add this to the previous one, right? And then this guy you need to add to previous guy, right? So obviously when it comes for adding these, obviously you add more numbers. If you have higher precision, you don't lose anything, right? But on the other hand, we are talking about addition, is not multiplication. If you think about this, if you go back to these additions, right, you see the difference, right? So see the difference between this, even this higher one, right? Even this higher one, or even this higher one, is lower than the multiplication, right? So I mean, if you increase the precision for addition, I mean, is not bad, right? So is bounded by your multiplication anyway. So it doesn't matter, and like better to have higher precision when it comes to addition. So I hope for everybody it makes sense, right? Why this kind of mixed precision somehow, because like having access to, so two things, like where this information exists and what kind of operation we do, and how this is related to the energy consumption of each of these operations and memory access. And that's why this mixed precision is useful, because like we have different types. And we also have like some concepts, batch normalization. If you use PyTorch on TensorFlow, you might have heard about it, and it exists in some of these APIs that use from these frameworks. Batch normalization is very simple, right? So when you remember for batching, right, during your training, you do batching, and you do a stochastic gradient descent through this batched input. Each input basically has some range of values. If you batch them together, basically batch normalization center the dynamic range of these inputs. Basically, for activation, specifically for each examples provide different activations, right? So for one example, the activation might like go from like minus something to plus something, these individual numbers. For another example, this would be totally different. So you have totally different ranges for each of these activations. So this, if you center each of these, if you normalize this across your batch, then everything is centered. When you do this addition stuff, you don't miss any crazy thing, because like if so, to give you an idea, that we talk about this here. Here, right? So especially when you have these floating points, right? So when you're on the upper range here, right? The kind of which, so between two different values, right? Either you go this way, so sorry, either you go this way when you round things, or this one, right? Because like you cannot represent this in between, right? No matter what, you need to go this way or this way, right? These are, we are talking about a very large number, right? And like this difference for large number doesn't matter. But when it comes to smaller numbers, this is huge, right? It really matters which one you end up. So, and that's why you see percentage, because this is accuracy when you average the whole thing. And then when you center this, you make everything even, right? So you're not having situation for some activation that are mainly here, some activation are mainly here, and treat them differently, right? You centered everything like somewhere, right here, and then do your calculation with the same scale. So you want to across your batch having the same scale, so you don't treat each example totally differently. You don't want to have a bias when you do this calculation with different precision, and that's why that's one of the technique useful when you do this batch normalization. You have a centered dynamic range where you can treat each individual examples in a similar way. And during training, you need to do weight updates. So these are the input activation. You have some gradient value. You have, again, multiplication here, right? And then you need to multiply it by the learning rate. You have another multiplication. And then once you have these delta W's, these weight updates, you need to accumulate it. So you have some addition in order to update the weights, right? So these are your previous weights, and you need to accumulate them to update the weights. So these are the operation for weight update that you have. And again, like you have, you're talking about different operation, different sizes, and how you want to consider different precision. And like one challenge that you might face essentially is that if you have very small, so imagine that you have very small gradient. You have very small gradient, right? And then like at the end of your stochastic gradient descent, typically you start with large learning rate, and at the end you want to converge it to very small learning rate. This is the way how you adjust your learning rate over optimization, right? And if you have this low precision stuff, if you multiply a small value here by a small value of learning rate, this multiplication again becomes very, very small. That this low precision would round it to 0, right? Because they are like very small value, and then this means that there is no learning. There is no so all of these delta becomes 0, and there is no learning. And this is one thing that you need to make sure you do it correctly. These are situations that happens in practice, especially this is about weight update. So you need to, when you do this mixed precision or lower precision quantized training, there are some challenges to deal with, essentially, to take care of it. And one way of doing this is called a stochastic rounding. This is also very interesting. Stochastic rounding is the case when you have like between 2 digits, right? Imagine between 2 values, right? Each of these representing 1 value, right? As a result of calculation, let's imagine that this W, and let's imagine this is 0, this is 1, 2, right? This thing would be 0, right? Would be very small, right? So in normal rounding, what you do is to round it to 0, right? And no learning. What a stochastic rounding does is that with some probability, instead of like normal rounding, then you always round it to 0 because this is closer to 0. With some probability, you round it to, let's consider P1, you round it to 0. With some probability, you round it to 1. So it's probabilistic or stochastic rounding, right? Like in let's imagine with probability 0.9, you round it to 0, probability of 0.2, 1, sorry, you round it to 1 or some other way. And at the end, you get an unbiased estimation of your weights. So expected value of the weight would converge to the true update, the true delta W, right? So this is again one another technique that that is super useful when you have these situations. Was this clear? It's very simple kind of rounding with terms of implementation. Is like taking a, you know, a random number and deciding which way you want to go. So in terms of, again, here what you see on the x-axis, different arithmetic precision from 32-bit float, 32-bit integer, 16-bit integer, and 8-bit integer. This is stuff showing the accuracy, the green one. This is showing the multiplication energy consumption in terms of picojoules, and obviously when you lose precision, you reduce the energy consumption. This is the trade-off space, right? So with all of this precision, you get similar comparable accuracy, that is fine, but you see that with this, you get a lot better energy consumption, right? Much better than these two guys that you have before, especially when it comes to from 32 to 16-bit integer representation. But on the other hand, like you don't want to also lose accuracy when you go from 16 to 8-bit integer, like you lose accuracy. And when you want to trade off, maybe this is the right way to decide. So within this trade-off space, you need to consider the right trade-off in order to not lose accuracy, but also reduce energy consumption quite a lot. For precision. For training, also, like when you compare, this is your baseline when you have floating point representation for all the stuff with no with no basically precision, mixed precision. This is when you use basically floating point 12 and 14, right? You see that they converge similarly, similar to the floating point, right? Representation. So these digits, integer representation also would converge the same way as floating point. But if you don't use, like for example here, if you don't use stochastic rounding, then during training it won't converge, right? It diverge because of the reason that I mentioned, right? Because you don't learn any new thing when you do this training of your network. Any question about this?
Yes, please.
Yep.
Could you please explain why it will diverge and the test error will increase if you don't use stochastic rounding again?
So basically, the key reason is that without by rounding to nearest one, like in this case I mentioned here, by rounding to nearest one, these things, this update that you add to the weights, right? So in order to update the weights, essentially you add nothing, you learn nothing from your new examples, right? So essentially there's no, especially later part, right? Because in a stochastic gradient descent, the scheme that you have, you decrease your learning rate over your training iterations, right? So here, like when you increase, when you go over your training epochs, you decrease your alpha, and this means that after some point, right, maybe like the initial iteration, that's fine, but after some point, right, so this is for testing, this is for training, right? After some iteration, since you are not learning, basically your error rate becomes high as a result of this training, because essentially you are not updating your weights for new examples. Does it make sense?
Yes, thank you.
So to summarize, with reduced precision, right? So we have reduced precision and also mixed precision, right? We talked about like why typically mixed precision makes sense. You can save memory, right? You have less things to store. You get better memory bandwidth, obviously, as a result of this. Like even if you store the same 16 million number of weights, but with reduced precision, you transfer less stuff across this connection for reading these weights. And for all of these mathematical operations with a smaller number, you get better efficiency, right? Typically for even 16 floating point, you can gain to 2x gain in memory and 4x in multiplication power in terms of energy efficiency. And like we discussed about this too, right? What batch normalization does, essentially centering around the same sort of scale, so you don't mess around with treating each examples differently, and also doing this stochastic rounding when it comes to training. So these are the techniques that you need in order to make sure that you do stuff correctly, especially when it comes to reduced precision model. Yeah, let's stop here, and then if you have any question, let me know. The plan plan is actually to continue again this stuff in two aspects. One is talking about the memory, also optimization with respect to memory kind of scenario that we have. Also with respect to quantization and model compression. So these are kind of topics that you basically might you might encounter in practice, and these are very useful topics, as I mentioned, when you want to deploy these models. Basically, this topic that we discussed today was basically building blocks, right? But how to do that is something else, right? How you want to like reduce this precision that you don't lose accuracy in a right way. That's the topic for quantization and model compression. And there are so many approaches, and this is a hot topic in machine learning currently, because these are relevant when it comes to, again, deploying machine learning system at a scale, right? When you want to deploy things in real small devices, right? And also like doing these stuff very efficiently. These are very, very hot topic at the moment in machine learning. And these are very important to learn about. And also like some of these, when it comes to memory, also important for designing chips, right? Designing chips that gives you knowing some of these are important to give you an intuition how to treat these different macro architecture when it comes for deploying machine learning systems there, right? And the kind of capability that you get out of these different essentially macro architecture that we are talking about. Okay, thank you guys. So talk to you soon. Good luck with your project. Ying will provide interesting tutorial. So hopefully this would help you to finish your project and deliver it very well.
Thank you.
Bye.
Thank you.